I'd like to thank you all for being present in this talk, and I hope that I'll let you walk away with some information about basically what we're trying to do to advance quantum technologies here at Wits. And so my focus of the talk today will be basically looking at how quantum technologies can be used for solving complex problems, and then seeing how this can then be extended to realizing communication systems that are unhackable. You've probably heard about some of these topics, but I'm just going to maybe focus more on what we're doing here at the Structured Light Lab to address both these two topics. So basically at the Structured Light Laboratory, our main focus is looking at controlling the internal degrees of freedom of light. And because light is fundamentally a quantum object, we can use it for many, many different applications, which basically leverage quantum sciences. But if we just step back and look at one of our optics tables in the lab, we have many beautiful looking lasers, and we can take these lasers and then give them different spatial patterns. And these patterns are basically all distinguishable, so we can tell them apart. And because of that, we can use them as an alphabet for doing many different things. The idea is that we give them these shapes and patterns using this technology that I'm showing here, which is basically used in projectors, but it has actually matured quite rapidly over the past few years, and now it can be used in optical experiments in a very controlled way. So with all these tools that I've shown you, ideally we'd like to see how we can harness structured light for looking at applications in quantum computing, quantum sensing, as well as quantum communication. And basically, I mean, you've probably already heard this, that these are basically the main three spheres of quantum information technology. And just to maybe remind you, I mean, the difference between this technology and our current technology, which basically uses digital information, is the idea that we can exploit quantum superposition. And just to remind you, in case you haven't heard so far, I like to think of superposition as if I had a particle that was going into a maze. And if the particle had to find its way out, and it's classical, it has to interrogate each and every unique path in this maze. And so probably it won't be efficient if it does it alone. However, if I use the quantum system, that would be very similar to pouring a bucket of water. And if you know water very well, I mean, water forms ripples, which can then spread out in space, and these would be waves that propagate. And so if my particle is basically water, so it's a wave-like object, it spreads inside the maze and is able to see all the parts in parallel. And so this is what we want to use whenever we talk about superposition, the fact that we can see multiple parts in parallel. Another thing is quantum entanglement. I'm not going to focus on it, but I'll just give you, again, another very intuitive explanation of it, which I like. Imagine I had two switches, and those two switches were synchronized, and I gave one to Alice and another one to Bob. And because these switches are synchronized, what ends up happening is whenever Alice observes a 1 on her switch, then Bob also observes a 1. And whenever Bob observes a 0, Bob also observes a 0. And if Alice observes a 1, Bob also observes a 1. And so these switches basically, no matter how far apart they're separated, are always synchronized. In quantum mechanics, I mean, it doesn't really work like this, but this is a very nice picture to use because in this system, if you look at it, I prepared the switches to be synchronized just like this. However, in quantum systems, the switch only knows what state it's in once it's measured. Before it is observed, we don't know what state it's in. And so this is another feature which is really unique to quantum systems. Okay, so what do you do once you have these types of switches or these types of objects that behave like waves? Well, it looks like we can start producing things such as quantum radar, where basically you can take one particle that is entangled and you can then use it to probe maybe an aircraft, which is hard to detect if you used a traditional radar system. And because the particle that you probed it with has another entangled twin, we can then use that to retrieve information about this object that we're trying to search for. And actually, China recently just developed a quantum radar that uses these principles that I just told you. They use entanglement to probe a very sensitive object. And it turns out that they can actually do this in distances that are close to around 600 kilometers. And so this technology is becoming real and is finding real applications. Okay, the slide isn't moving. Has the slide changed on your side?
I'm still
Okay,
seeing the, oh, there we go. Solving
okay,
complex
great,
problems.
great. So now, that one problem that I showed you before is complex in the sense that we're trying to detect an object that shouldn't be detected. So that would be an imaging problem. Now let's look at a computational problem. Now, what if I was a salesman that was perhaps trying to find an optimal path that allows me to maybe optimize something such as cost, okay, or energy? And usually, these types of problems in computing are combinatorial optimization problems, and they are NP hard, which means that the solution is easy to verify, but finding it is not very easy. And so quantum computers are actually designed to solve such problems. And if you spoke to an applied mathematician, they take this type of problem, so a problem where you need to search multiple paths to find your solution, and they'd map it onto a computational graph. And from this computational graph, then they can then map it onto a matrix. Now, in quantum computing, matrices that look like this one here, and an applied mathematician would say that this is a symmetric matrix. For us in physics, these are usually associated with matrices that describe the energy of a physical system. And so the idea is that you can take a computational problem that is quite abstract, and then you can map it onto an energy minimization problem where the problem is now observed as if it was representing a physical system. So instead of searching for the paths for this person to walk through to minimize their cost, we map this problem onto an equivalent physical system and then ask, how do I tune the parameters of the physical system until I find its lowest energy state? And so then you can see that energy here is very similar to cost. And so this is what people in quantum computing are basically exploiting to solve problems. Now, another example of a complex problem, and actually this was one of the early examples of quantum advantage. Well, I shouldn't say quantum advantage, but it was an example of quantum algorithms that were designed to show that quantum computers can solve problems more efficiently than classical ones. And this example is called Grover's search algorithm. So imagine if I had an unstructured database. Okay, these are the elements in my database. The equivalent picture for it is, let's say I had a picture here of similar looking cats, and I need to find a specific one out of all of them. Okay, again, if you wanted to do this brute force, you go search for them one by one. However, Grover's algorithm, basically internally what it does is it can mark these elements. So for example, it can mark this cat here. And then what ends up happening is the algorithm is designed so that it amplifies the probability of finding this specific cat which we're searching for. And so then this can be used to search for elements in very big databases. Now, in our lab, we solved similar problems using structured light. The idea is using those patterns that I showed you before, I can use them to actually probe objects and find information about their features. This is similar again to having some object in three-dimensional space. And basically, if it's a quantum object, for example, the only thing I can do is perform projections on it. And projections would be similar to looking at the shadows of this object in my 3D image here. And so then from these shadows, I design a computational algorithm, which then allows me to basically use the information to work out what the shape of the object is. And so then the idea is you would then phrase this as an inverse problem. I have some features about the objects that I've probed, and I'd like to use them or invert them to find out what object they correspond to. And so in quantum information sciences, this is usually called quantum tomography. And if you're someone who works in something like paleontology or topography, this would be computational tomography, the art of probing things and probing objects with different probing states, and then using the information computationally to retrieve the object features. So what we want to do is basically probe the object using quantum signals. So then I'd be using quantum sensing to do this. And then we'd use a computational algorithm that is ran on a quantum computer to actually figure out what the shapes or what the underlying system is. Okay. And again, this can be done for objects, it can be done for physical systems, can be done for anything that I have the ability to probe. As long as I can probe and measure, I can use this scheme. Now, why would I want to probe things with these patterns? Remember, I told you these patterns are basically a large alphabet for encoding information. So here's an example. This shape that I have here is basically a spatial pattern, and someone might argue that it looks like a lion or it looks like a bear. You can choose. It turns out that, well, we actually produce this pattern here by adding up these individual patterns that form my alphabet. So what I have on the left-hand side can be the unknown object. And then on the right-hand side, I want to know what combinations of patterns produced this object. And so the challenge with this is there are many patterns to search through. And so if you're doing this in practice, you actually have to do many measurements and wait for a long time to gather the information that's needed to find the object shapes. And yeah, usually this depends on the number of parameters. So it depends on the number of patterns you're searching with and the number of particles that you're probing with. So what do I mean by particles? I mean, so if I, for example, was using an entangled system, so my system now is like very similar to those synchronized switches. So instead of synchronized switches, I have two particles that have synchronized patterns. So they are entangled in terms of the patterns. So if one particle has this pattern here, the other particle has a different pattern. And sometimes we like to take one particle and then probe an object with it. And because they are entangled, the other particle inherits that object information. I believe you must have heard about this, and because it's called ghost imaging. Okay, so what happens is, I mean, I need to prepare this entangled state. The particles are synchronized in their patterns, and then I need to use the outcome measurements to then say something about either the entangled system that produced these patterns or the objects that they're probing. And so if I only have two patterns in my alphabet and two particles, usually a measurement matrix would then contain about 36 elements. And as you can see, I mean, this scales very badly. So if I increase the number of particles, in fact, I'll end up having more and more measurements to do. So what we want to do is to take the measurement data, so the information that we get while probing the system, and then we send this into a quantum computer. And basically the quantum computer will search through the parameter space and then give us the solution, which is the underlying object that maps onto the measurements that we observe. And so to achieve this, again, we take the input data, we represent it in a way that the computer can understand. And then what we do is we set up a cost function, which is basically a function that we use to check if we're getting close to the solution or not. We map that to the energy function, just like we did when we were solving the traveling salesman problem. And so then the idea is we're going to then probe the quantum computer to search for the states. And then on the classical computer, we'll then decide what new parameters to probe. And so this is actually called a variational quantum algorithm, where you're basically optimizing parameter selection on a classical computer and then using the quantum computer to probe for whether you have the information or not. And so as you do this, you keep searching and searching until you're able to minimize your cost function. And so if you do this using our patterns to probe the system and then extract your measurement data, we find that you can actually do this quite accurately for a two-particle system where your alphabet only contains two patterns. And so we could actually do this quite reliably with our system. This was done by one of my students, Mwezi Koni, who is now actually continuing this work in his PhD. Okay, so while doing this project, we realized, well, I mean, the optical system that generates the data is itself quantum mechanical, and the quantum computer is also quantum mechanical. Why not just remove the quantum computer and do this directly on the optical system itself? Because, for example, if I'm maybe imaging biological samples with these patterns, maybe I don't want to spend too much time reconstructing the features because the system is too dynamical and evolves quickly, and maybe I want to do this in real time. And so we asked ourselves whether we can design an optical system that allows us to perform both the data encoding, so probing the states, as well as probing the information about the states in real time. And because we're doing this using photons, we can actually do this at the speed of light. And the answer is yes, we can. And so what we do is we prepare our photon fields, and then we have spatial light modulators, which perform the data encoding. And then we have a second spatial light modulator, which we then program to do the processing. And because light, as it propagates in space, essentially applies a Fourier transform, which is an essential computational operation that you need whenever you do image processing and such, we find that, well, lenses simply do this Fourier transform for us. And then all you need is basically a detector where you read out the result after light has basically done the computation for you. And so we did this in a series of papers where we showed that you can use this scheme to emulate quantum computing. And also the underlying mechanism that basically allows the system to do computing is basically it's that the system itself looks like it's performing matrix multiplication, but in an analog manner. And we also showed that we can repeat the variational algorithm that I showed you before on the quantum computer, but now using our optical system. And so, because I can't go into too much detail on this, I'll just show you this optical system actually learning in real time. And so what happens is this is the data that's sent into the first spatial light modulator, and then the second spatial light modulator is used to search for the underlying solution. And as you can see, the parameters, which are shown here in different colors, over time reach stable values, which actually are the underlying solution. And so this shows that we can effectively do the same thing that you would do on a quantum computer in an all optical system. And this was done by also Mwezi and Hadrian, who are also my students here at the Structured Light Lab. Okay, and now, I mean, as you can see, the experiments that I've shown you are basically simple tabletop experiments. And everyone playing in this game doesn't just want to do tabletop experiments, we want to solve real problems. And one of the problems that everyone is trying to solve is Shor's factoring algorithm. The idea is that, I mean, Peter Shor a few years ago basically demonstrated that if you have access to Fourier transforms or quantum Fourier transforms, you would be able to solve the problem of factorizing large numbers into their primes. And so this is actually also a very difficult problem to solve. And Peter Shor showed that you can do this using quantum computers. Now, the thing is, if I gave you a 200-digit number, if you had to do this to find the prime factors of such a number using a classical computer, it'll take you about days or weeks. However, using Shor's algorithm, you can do this in seconds. Well, you could argue just increase the number of digits that you have, right? And so let's say maybe you now looked at a number that has about 1,000 digits on a classical computer. I mean, you wouldn't actually be able to find these prime factors, at least in the age of our planet or a single lifetime. But on a classical computer, you can actually do this in hours. And so because this factoring problem is basically the main problem that's used to design our encryption algorithms and specifically RSA encryption, our communication systems might actually be hampered by this. And why is this the case? Okay, if you look at optical fibers, which are basically transmitting light and allowing you to have internet, if you bend one of them, you'd find that actually light leaks out of them. And because most communication systems use on-off keying, where you're basically modulating the intensity of the laser beam, so switching it on and off very quickly, if I could get this light and I observed it, I'd actually be able to know what information was encoded. And now if I have access to a quantum computer, I'd be able to find what keys are being used and I'd be able to hack such a system. The solution, of course, has been to also look at quantum systems, since the security, if you use quantum systems, is actually provided by nature itself and not by the difficulty of solving a very complicated computational problem. And the idea is that I think you must have heard about this as well. You can use what's called quantum key distribution, where you prepare single photons, so single light particles, and then you encode them with uh, your desired alphabet. For example, if you were using polarization, you'd use these two bases. So your photons would have polarizations that are horizontal or vertical, or you could have a rotated basis, which is diagonal or anti-diagonal. And so Alice and Bob would randomly choose between these two bases and then exchange photons. And then from those photons, they can actually find that after they perform a sifting procedure, they'd be able to have a correlated key. And here the idea is that because nature itself, I mean, quantum systems are quite fragile. If you disturb them, you change them. If an eavesdropper tried to hack the system, they'd actually introduce errors that are detectable. And so because of this, it means that this system is essentially quite robust to having eavesdroppers, since we can detect eavesdroppers. And if an eavesdropper tried to extract information, it turns out that it's actually quite difficult to do it because of this um, because of the no cloning theorem. So you can't really copy information in quantum systems. And because of the uncertainty principle, you have to know what state the photons are prepared in order to extract information effectively. However, the issue is if you look here, the encoding alphabet is actually two-dimensional. I either have something oscillating upwards or oscillating in the horizontal direction. You might think that this is a unique basis, but actually these two bases have a large overlap. And so I'm always only restricted to a two-letter alphabet if I'm trying to build encryption keys using this scheme. In our lab, we've been looking at playing around with spatial patterns of light, since they're also a quantum alphabet. And because we have more than just two letters in our alphabet to encode, it means that we can actually increase the information capacity of these systems. Now, the challenge is if you have many patterns, then you need as many detectors as the patterns that you have. And this can be challenging. And so if you read most of the papers that basically look at quantum key distribution using spatial patterns, a lot of them use sifting operations. So they only probe one pattern at a time and are not able to actually probe these patterns in parallel. This would be what we call a deterministic detector. Now, we've been looking at solutions for this, and the solution that we've been looking into is to maybe look at a new regime of optical computing, which is called optical diffractive neural networks. The idea is that if you prepare a laser beam and you send it through a series of obstructions, the obstructions actually perturb the beam as it propagates in space. And so if I can control how the perturbations look, that would be similar to controlling the learning weights of a neural network. And so then I can then now start sending light patterns into this diffractive optical neural network. And at the end, I can then use it to example classify what spatial patterns my optical fields had. And so our system, which we've been developing with Hadrian during his master's, basically looks at precisely doing this, where you have Alice who has her alphabet of spatial patterns um, at the single photon level. Each of them are distinguishable, and Alice can then send them to Bob. And let's say Alice chooses this one here that encodes the letter L is equal to 2. If we send this to our diffractive unit, the diffractive unit then maps it onto a unique position that can be then sent into a single mode fiber. If we do this for all our patterns, then basically all these patterns land at unique locations. And so in a way, we build a system that classifies these patterns by mapping them onto bins in space. And these circles that you're seeing here, this geometry basically tells us, I mean, basically resembles optical fibers, a bundle of optical fibers that are sitting in space, and each of them would be receiving light in these different locations. And so we could then be able to detect whether Alice sent the first spatial mode or the third spatial mode with a single click faster than what people traditionally use. And just to show you, this is an example of the system actually learning the parameters, or this is us training it to maybe be able to detect about 2 modes. And so as you see over time, we can actually use a supervised learning procedure where we perturb our optical system until it finds the mapping that allows us to distinguish the states we're encoding. And currently, we've been able to actually design a system that's able to detect close to about 9 patterns. And we're still trying to push this even further so that we can maybe access many, many more modes and so that we can have a very large encoding alphabet. So in general, I reached the end of my talk. I've shown you that there's many applications that can leverage both structured light, quantum computing, quantum sensing, to actually realize new modalities of solving complex problems. And if you'd like to come play around and also join in on solving such problems, please come visit us at the Structured Light Laboratory. These are the amazing people in our lab that contribute to doing this amazing research. You can't do it without people. And yeah, with that, I'd like to thank you all.